Okay, so thank you everyone for joining, and thank you for McEwen Mining for allowing us to do this, and Nathan who actually organized everything. I met Nathan at CIM last year. My name is Sohail, and you can remember it as so much hail coming from the sky, so it's Sohail. And I've been in this industry in mining for around 6-7 years. I did my grad studies in controls, fault detection, modeling, and advanced process control. And Matt is also here with me. He's a founder of a simulation software called Ideas. He has been with Andritz for a long time, and he retired. And 3 people replaced him. One of them is me, so 3 of us are replacing Matt. But he's still with us as a consultant, so I'm very happy that Matt is here. He's my mentor as well. Okay, so today we're going to talk about digital twin, but before I start that, just for 1 or 2 minutes, I want to tell you who we are. We are Andritz, and Andritz Group has different core industries, pulp and paper, hydro, metals, and also mining. We are global, and our headquarters is in Austria. But what particularly we do for mining industry and mineral processing is basically with Andritz Automation, which is a global also again organization. We provide all the electrical power engineering, control engineering, which is vendor neutral. And then after that, we have optimization and advanced process control, which is our proprietary softwares. We do the simulation and modeling, which mostly we're going to talk about that, and remote monitoring and controls. And on top of that, that's the cherry on the top of our cake, which is the industrial Internet of Things. But we also provide a lot of equipment in mining. So separation equipment, solid and liquid, like thickeners and centrifuges, filter presses, as well as specialized pumps and furnaces for dewatering, and also the hydropower. So we provide equipment, so we are providing the equipment knowledge as well. But let's start the talk. So picture this. It's 3 a.m. in the morning. You have one person on site in your mill, and then one of the pumps downstream just fails, or something fails on downstream, right? What usually do is the operator starts to handle that, right, somehow, because the downstream fails, it's going to back propagate all the way up. You don't want to lose your production. You don't want to lose your recovery. What if an artificial intelligence knows exactly how to use the recirculation, how to use the retention time, how to change all the set points so that you will end up having the least amount of loss of recovery, the way without letting the failure downstream back propagate all the way up, because it knows exactly how the mill is working, right? Is it sound very fictional? Well, we will find out. Not anymore. As Rob said, these things are out there, are happening right now, right? So we will focus on digital twin today. There's a lot of different buzzwords, and I'm happy that Nathan showed the graph that actually this one got to the 10 important buzzwords that is coming out. A couple of years ago when I heard this buzzword, I was like, is this a hype? What's happening? And then this is not something that we invented. I looked into it, and basically NASA has been doing this all along. We've been doing this all along. In 2010, NASA brought the term digital twin as part of their strategic improvement for the years to come. But what does it actually mean, right? So let's put it out there. In the digital twin, simulation is a core functionality for the system to improve something, right? And it has to be valid for the entire life cycle of that process. And it also needs to have a direct linkage for the operation data, right? So there are core important things that distinguish digital twin from what we have been doing maybe 10 years ago, 15 years ago. And it's that the entire life cycle and also simulation being the core of the optimization and providing value. Because at the end of the day, you want to bring more value to your plants, right? But this is my own take on where the digital twin and all other things that you keep hearing for the last couple of years go together. So the industrial Internet of Things or Industry 4.0 and all different names that are out there for that is a different topic. I had a talk a couple of months ago about it, a couple of hours. But that is also integrated with the artificial intelligence and also digital twin. At the end of the day, you want to make decisions, right? So you want to provide value. Somebody has to make decisions. That's where is lacking in mining industry. How do we make decision automatically, right? That's where the artificial intelligence comes in. But then that artificial intelligence is very integrated with machine learning technology, with big data analytics, and also simulation, right? Everything is overlapping together. So, and we will see how important the digital twin weight is. Now, my question for you is, what if I tell you there's a dark secret about artificial intelligence? Which pill you're going to take? Do you want to know about it? That blue one is the Andritz blue pill. So, and which pill do you want to take, right? What do you want to know? What is actually behind the scene happening? There are a lot of things to consider when looking at the artificial intelligence, which is basically the promise, right? So, first, let's see what the artificial intelligence is. And let's be a good engineer, like every engineer. And this is a new concept, and we want to learn it. So let's open Wikipedia and see what it is. OK, we're going to read it. Artificial intelligence, or AI, is intelligence displayed by machines in contrast with the natural intelligence displayed by humans and other animals. Now, here's the interesting part. In computer science, AI research is defined as the study of intelligent agents. So you need intelligent agents, right? And those intelligent agents are any device that perceives its environment, right? And takes actions. That's what's missing. We need to take action. And then maximizes the chance of success. Now, here's the key, and that dark secret that I was talking about. Perceives its environment. You need to train your artificial intelligence, right? So it's not going to born today. It's like a child. A baby is born, and you want to take it to operate the plant. Can it do it? No. It has all the capacity to do it, but it can't, right? So he or she, I shouldn't say it. But anyway, so the artificial intelligence needs to understand the environment, right? And that environment is very important. How do we make that environment possible for our AI, right? There are different methods. There's a data-driven methods. There are first principle methods, and we're going to talk about that, right? So I want you to keep that in mind. And then we're going to talk about how we make that environment. So they might say, OK, I'm going to use the data that is coming from the plant, right? I'm going to look at the history of data. I'm going to use machine learning algorithms to, build up some analytics for me, right? That's great, right? That works. But there are things to consider. So look at this graph. You have your process plant, and you have your plant operation, right? You have your operation point. First of all, the promise of all these technologies is to start from all the way from the beginning, the entire life cycle. So there's a life cycle of your design and process that is not even generating data. What are you doing with design, construction? You don't have even the operation data yet, right? So that's the first thing. But let's say you're actually operating, right? So you have different modes of operation. You have the nominal operation, your day-to-day, every hour, every second that's happening. And you want to stay in this, right? All the promise of hiring the good operators, hiring engineers is to stay at this zone, right? But you never can stay at this zone all the time. You always have disturbances. You have ore grades, changes, and everything else, right? But there it comes, the big problem, when things fail, right? But then the whole entire promise of your people are to make sure that that doesn't happen. But it does happen all the time, but it's infrequent, right? What are you trying to do? You are trying to use technology to handle the problems when these infrequent problems happen with disturbances and rare circumstances, right? That's what you're trying to do. But first of all, you don't have enough data for it. So when you use the data driven methods, right? There is a concept in machine learning is that when you have data for one particular mode, all your analysis will skew inside that mode because you have a lot of data for it, right? So when you use that, you are putting a lot of data in your nominal operation, but you want your artificial intelligence to be perfect, reliable on the places that you actually don't have data for, right? Also, there's a lot of times you can't measure the data, right? Can you measure the sag mill charge? Can you do that? No, you don't. We don't have a sensor to measure that. Can we measure the scaling inside our evaporator? No, we don't have a sensor to do that, right? But those are very important information that we need. So basically, you end up with islands that will never converge in your algorithms. So what are we going to do? So you will have the data unavailability and a lot of unmeasured variables. We will not have a complete picture. So what are we going to do? We have to complement this. How are we complementing it? We will make a simulation and models of the process that are not based on the data. They are based on first principle models. They're based off the equipment data sheets, but based off the physics and the fundamentals that those equipments and processes work, right? By doing that, you will start filling the gap, right? So again, this is not this method or that method. These two have to go hand to hand. They are complementary. When you do that, then you start having the whole entire picture. And that's when you start having your artificial intelligence perceive its environment. We are making the environment ready for our AI to work, right? And I'm sure that you've seen this, that there are really nice AI algorithms there, companies that providing that. The promise is, give me all your data, I will provide the value for you. That's great, but that's the ugly truth behind it. That's the ugly truth. Okay. Now, just quickly, this evolution of the simulation. So basically, so far, the case that I'm making is that fundamentally, from ground to the up, we need to have good models, we need to have good simulation to make the digital twin happen using the data coming in. So simulation all started with the stick and sand when generals wanted to go to war, right? They would put this is the mountain, this is the river, we're going to go from here and there. They were simulating everything. But then it all evolved to becoming a design tool as we know it now. And now we have the digital twin. So what are the concepts of the digital twin that makes it different from a design tool from simulation? Here is a graphical representation of the hierarchy that's happening that makes the digital twin happen. So you have the simulation and modeling software, right? That's when it was used as a design tool. But then here is the part. You have the execution and communication platform that allows you to run this model as many times as you want, as fast as you want, and connects that to your operation data. That connectivity is the key, right? So before we had the island of the simulation happening and then done, but now we are connecting it to the real-time operation. But then for doing that, that model has to be really good, right? So fundamental from down to the up. Then we are able to connect it to the other softwares and operator interface. But look at this platform as your smartphone. So you have your smartphone, and now you have different application that uses this platform for different reasons to provide value now. One application can run this simulation many times to make the fault footprint of your abnormal condition, right? So when you see that, you can see which of these abnormal condition actually matches your data right now. We use that for detecting leakage in the 40-kilometer pipelines, right? Where is the leak in the pipeline based on the pressure and flow portfolio of our pipeline right now? Where is the leak happening? Also, you can have another application that runs this simulation connected to the real-time operation data and then reconsolidate the data with your model so that you can extract information that you can't infer easily or your measurement is not reliable. Right now, we are using that for the density visual instrument. So we get the different information from the plant, we infer the density of my slurry going up inside my...
So,
yes?
So when you're doing your 40-kilometer pipeline and you've got the hole,
Mm-hmm.
have you taken data for the last 10 years, knowing where the holes were, and put that into your model first to then run the simulation?
Okay. So the question is, do we need the last 10 years data inside the model to make the leakage detection? No. The answer is no, because the pipeline model is based on the first principle model of the thermodynamics that's happening and all the equations. So I look at the leakage going out and I look at the pressure portfolio and see based on this differential equations where the leakage is happening. So I don't need, that's the promise of having the simulation. I don't need the data. I will tune it if I have the data to make sure that my model is exactly representing the model of the pipeline, but I don't need the last 10 years data, no. Okay. Another application is that I will use execution platform for checking all my logics in my control system. These examples are the ones that I'm going to show you later on in action. And you can see this is not smokes that we're talking about. This is happening right now. Okay. So again, we're talking about simulation and modeling and simulation and modeling. So what do we mean? There are different levels of simulation in mineral processing. There are macroscopic level, which basically says I'm going to look at the plant-wide, I'm going to look at the equipments, I'm going to look at my pressure network, and all that. There's a discrete element simulation and molecular. What I'm talking here in this talk is the macroscopic level, right? I'm not going to the discrete element and molecular. So how do we model the mineral processing plant, the mining plant? There are different modeling techniques, and you know that better than me. I am not a mineral processing guy. I'm not a chemical guy. I am controls and I'm in controls and using all these technologies. So there are physical differential equations, chemical partition, conservation of the mass and energy. There is kinetic and empirical. But we're not using all that in all different sections of the plant. For example, in the mining and material handling, we are using physical and conservation laws mostly. And then in the comminution area, the partition theories and partition modeling is added to the conservation and empirical models, right? And then that allows us to model the sag mill, the ball mill, the flotation, and all, the hydrocyclones. And then on the flotation and thickener, we are using the chemical and kinetics a lot more, right? You want to have all the chemical reaction that is happening, what is the rate of the reaction that is happening, what is the sedimentation theories, and all that solubility, and everything has to be taken into account. So that is going to be used as well. But the model itself is not the only factor for your digital twin, right? There are more factors. Now, it's the software that you're going to use for your digital twin has to have scalability, right? You want to model the entire mill and mining process so that you can connect it to your operation, right? It has to be scalable. We're not talking about just one equipment here. We're talking about the whole plant. You want to have the connectivity. You want to be able to connect it to the real-time operation. all the models have to be state of the art. So the software you're choosing and you want to use has to have all the information that is available right now. Also, the algorithms that are going to make the convergence of your model happen need to be fast and stable. You never can crash, right? You are running this in real time. You never can crash because, see, that's a problem with the artificial intelligence. Humans are allowed to make mistake, but somehow AI is not allowed to make any mistake, right? So it has to be 100% reliable, but then humans can be 90% reliable. That's perfect, right? But AI can't. So you have to be always reliable, right? But the last but not least is the fidelity, right? You keep hearing this fidelity, right? And I'm going to talk about the fidelity a little bit. What does it mean? So fidelity, the definition is how much does the model or simulation represents the reality, right? How close we are with the reality. And there are different factors that can let us measure the fidelity, right? But how do we make the fidelity happen in our simulation, right? So we need to get metallurgy and process data, add the mechanical and physical values, plus the control and logic. All of that have to be together hand to hand. So there's not just metallurgy or process. So even we also put the human characteristic and the intervention, right? So for example, for one of our customers, we had the underground mining and the shift changes, right? So that shift change and the people going and actually being late on the job and all that had to be inside the model, right? Otherwise, the model is not representing the actual reality, what's happening. All the PNID information, all the equipment data sheet, and everything has to go inside there. So we're not talking about just a metallurgy software. Otherwise, it's not just going to happen. Okay, Matt is here. Later on, we are able to show you this, some live demonstration of the simulation if you want to after. But I kept talking about the digital twin promise is about the entire life cycle of your process, right? The entire life cycle is, I'm going to start from the feasibility study all the way to the maintenance and operation, and I'm able to provide value with my digital twin, right? Let's see how that works. On the feasibility study, you can run the simulation, you can run your digital twin so that it decreases your CapEx and OpEx on your design, right? I'm gonna have a design that have the lowest amount of OpEx possible because I wanna save the power automatically. Like, tell me what equipment I should use to save the power for the 10 years of my operation for all these ore grades. Is that the dream? No, actually, right? It's actually an easy concept. It's been happening, right, for a couple of years now. On the detailed engineering, I want to validate all my PNIDs before I start construction. Run that, tell me if this design actually going to work with the upset condition. Is my valve and my pump are actually right for this job? Because I don't want in 6 months to realize that, oh, we didn't consider these extreme conditions and it's not working anymore. So I want all my control system to be checked out before and run that automatically and tell me if there is anything wrong with my control system before I even commission my plant, right? Then I want all my operators to be trained, right? Run the simulation like an instructor and the simulation that has been in the aerospace, right? It's been happening in the mining as well now. Then that's where it's very, very new now. Now I want to connect my simulation and models with the data coming from the operation to the real-time operation. Now I want to see what are the values that I'm getting. I want to see the virtual values. I want to optimize based on the models that I have, right? And what's going to be, where my plant is going to be in the next 10 hours, right? Am I going to hit any of these constraints that I have? if I make this decision right now for maintenance, in the next 5, how much time do I have before I start up this particular area, so I can fast forward, see what's happening, come back, and then do the decision. Okay. So for the rest of the talk, so far it was all concepts. So, and I know everybody's like, oh, these are now cool concepts, but are we doing it now? Yes, we're actually doing it now. So I'm going to talk about a couple of examples that people in different mining operations are using, and it's been happening. One of them is automated design, right? So on the feasibility study, we can automate the circuit design so that we know for the entire lifespan of our mine what will provide, what design will give me the least amount of power usage, right? And which equipment I should use for that design. Now, all the engineering companies do that, right? So this is always like Uber came and everybody was like, but we have taxis. So why do we need Uber, right? And then you see the difference. Yes, our engineering companies do tell us which design gives us a better power saving, but this is way more cost effective now because it's all automated. Everything is automated, everything is integrated. So I can run it many, many times, many different scenarios. How does it work? I have different options. So I have this, I have the model of my plant, and then I have different options that I want to try. So I want to try all the throughputs with different throughputs that I have, with different ore grades that I have, and then I generate the scenarios. So permutation of all different scenarios that might happen, and then I run the simulation models. I collect all my data that is important for me, put them in tables, analyze the result, and then connect it to the database. So now, not only I have designed it, I will look automatically to the database of the equipment providers to find which equipment will give me the best result that I'm looking for, that give me those results, right? So that will be the starting point of the engineering if you want to. And automatically issue reports. Okay, so I'll show you in the action, live in action. Now all these videos that I'm going to show you are available on YouTube, and you can see them. Please come and see me after, get a card, and I can send you the links for it because it's not easy to find. Okay. Okay, so let me first, how much time do we have? Oh, okay, I have time. Okay. Okay, so this is example of a lead zinc complete circuit of the lead zinc mill processing with mine and crushing, grinding, and flotation all the way to the tailing. And we have all the models in there, SAG mill, ball mill, and everything. Okay. Now here I want to have an automated design of different scenarios that I have. So are permuted, and these are all my different scenarios that I want to run, and I show you in action. So then automatically let me put it here. Okay. Then automatically I can run all these different scenarios, right? Everything, and you can see it's running, but it's a little bit slow because I don't know, my computer is running a little bit slow there. Okay. And then I can generate all the reports that I need, right? So I'll generate all the reports for power. So for example, in this study that we did for one of our clients, they wanted to know the SAG mill inside the entire circuit and the HPGR, when they put it with all the PSDs and everything, which one in 10 years will use less power, right? And those are and with the throughputs that we have, right? So we get all that, but then there's a really interesting catch here, is that when you do the when you have the model, you can get every information that you need. For example, the PST for entire circulation, right? Your mail charge, your other information that you never can get and you can't analyze, now with your model is available to automatically analyze and see which one gives you a better value for your operation. And you can decrease your CapEx and OpEx. So another customer is looking to work to see how to decrease the amount of the metal usage for the design of the pipes and everything else, so we can minimize that design, so we can decrease our their capex. Okay, and then you can make all the reports on what is my pressures everywhere, what are my fellows, my temperature, and you can also use the analytics and artificial intelligence to make the decision. Okay, so that's one. Now the other one is the failure analysis. So basically, now I have my digital twin that has all my models, all my circuit. I have all my, it's connected to my control system, right? And it's connected to all the data sheets. Now, I want to see if any failure happens inside this plant, what are the consequences? So this is a hazard study that we do, right? But we all been to the hazard studies and we know how tiresome it is. And it's never perfect because it's really hard to look at every possible scenario, right? But now we are doing it automatically, right? So not only that, I can see all the transitions happening as well, which we cannot see it before, right? So what are the transitions? So, and the idea is very simple. I have a very high fidel model that I connected to my execution platform, and I will run it with different scenarios. So, oops. Okay. So, it's not. Okay. So here's the live demonstration of that. Now, one thing that we didn't even think about it, and then one of our clients told us about it, and we were like, wow, we did not even see that, is that his problem was when any time that I change any logic in my control system, I need to test it. I need to make sure that change in the logic will not have effect other places. And he said it was very tiresome and hard to have my people to test it. I can't test it on a real plant. So then he saw this and he was like, oh, now I can run it automatically every time. Any changes, I can do this failure analysis and see if it's actually improving anything or if it's not, right? So let's see it in action. So now this is the entire plan simulated, and you can see the model behind it with the HMI in front of it, right? And the model behind it. Now the analysis here is to look at the scenario that we made here for this demonstration is to look at all the pumps in that plant failing. And what's going to happen with the next 5 hours, how the control logic and control system will react to that failure, how all those interlocks will behave, how my every characteristic in the plant will change, how are we going to react? Are we actually protected or not? So what's going to happen, right? Let's show it in action. Here. Okay, this is a good shot. Yeah. So you can see that our platform is running, right? And then it starts going over all different scenarios one by one, failing a pump and see what's going to happen in the next 4 hours, right? And capturing all that data. But we don't need to wait 4 hours. We just run it in like 2 seconds, right? All that 4 hours is running 2 seconds, right? So we can do all that and let it run for, I think this is like, for the whole entire operation, we had to run it for like around half an hour to get all the data. Now, the thing is, these become very cost effective now because the human is not doing them. You just build it once and then it's just you're going to run it as much as you want. Okay, so let's look at the results now. And then you can look how every aspect of your plant behave to those failures, right? So did we go over any high limit or low limit that is important for us? We can then put values on those and then penalize on the different scenarios and then understand which failure is more catastrophic than other failures, right? And prioritize and use that to actually prioritize our alarming. One thing that one of our clients showed me, and I didn't think about it either again, was that, I'm going to use this to show the operators how much time they have to react to certain failure, right? If you don't react in the next 10 minutes to this alarm, see what's going to happen. This is going to happen, right? And then they can see it. And then after that, we can look and see which failure is actually has the biggest impact and biggest impact in the plant and the prioritize. Okay. Let's go to the next one. So far, we use the idea of digital twin for automated changes and design. Now we're going to talk about the digital twin in the connected to the real-time operation to provide value. The example that I want to go over today is on the density virtual instrument, right? So in the mills, ball mill, the sag mill, the ball mill discharge going to the hydrocyclone, right? The hydrocyclone box density is very important, very important. That if you keep that density very close, then you will have the PAD variability very small, right? And when you do that, then you can optimize. So that density meter is very important. But the density meter itself, it's not reliable. It's nuclear, so you have always those radioactive problems, and it's always expensive, right? And usually what we saw with the clients is that they don't rely on it, like after a couple of while, right? So but our control strategy for optimization is based on that density value. So what we're going to do, we have a very high fidel model of pumps, cyclone, the pipeline, and everything. We put it together, we make the digital twin of that circuit, and we connect it to the real-time operation. As soon as I get the data, I use reliable data, for example, power of the pump, speed of the pump, pressure, and other factors, data that I get from the plant. Now I'm able to infer the density and the flow in real time, right? Let's see. And what are the benefits? Well, if I have a density meter already, then I can check it with if it's reliable or not. If it goes out of tune, I can make alarm. If I don't have it, then I can just actually use the density. Because it's expensive, now in the plants, we don't put density meter everywhere. But when you have the virtual instrument now, you can virtually put it everywhere. Now you look at the density. So some results. This is a 1 week result that we had on one of our plants that we put it there, installed it there. Red is the physical and blue is the virtual instrument. And you see for the 1 week, the density meter was tuned just recently. So we thought that we're going to rely on it. And you see that we were always on there. But then this is the interesting results that I like to share. So this is an 18 hours operation, right? The density meter is yellow, inferred value is green. You see that when there is a nominal operation, these two were going well, there was no problem. But then when the density actually going down, right, the density meter failed, and then the density meter was not valid for like an hour, but then our virtual instrument was valid. Now imagine if your control system tries to control based on the density meter, the control system stops, right? And if you don't control based on the density, then you will not get the very good PAD. So these are all connected. Now this is an interesting part here. So the plant had a shutdown, and then they started up. As soon as they started up, we found a bias between what we are seeing and what the density meter is seeing. Now, where is this bias coming from? Then we looked at it. Oh, guess what? There's a sanding happening in the pipe, right? And because of that shutdown, right? And now we are able to look at this bias. First of all, calculate how much sanding is happening, close the loop into advanced control system, increase the pump speed to actually get to actually make those sanding go away if we want to. So there's this, if you already have a density meter and your virtual instrument, now you're able to protect yourself against that sanding. Okay, where are we going to use it? Anywhere basically in the line that we need to, we're going to use the density meter. You can put it on the underflow thickener, you can put it on your flotation, you can put it on your comminution area. Okay. Conclusion. So, what is the promise? The promise is optimization. That's a big promise, right? And now we're talking about artificial intelligence. That's going to bring us there, right? But then we talked about artificial intelligence needs that environment, needs that training. And if it doesn't have that, will not bring that optimization, right? So, here we have the digital twin to provide that environment, but that digital twin, the fundamental part of that digital twin is the modeling and simulation. So basically, it's what I like to emphasize is the ground to the up approach. You start from the top, you never have good result because your fundamentals are not working. It's like control. They come and say, hey, I'm going to put a very nice hierarchy control on top of your plant, and it's going to optimize things for you. No, it won't, because first you have to make sure that your fundamental control system works and everything is stable to change the set points. You don't make sure that that happens, then we'll have problem. So the digital twin connected to the real-time operation and allows us to get benefits for the entire life cycle of the plant.